All right, we're on Unit 8, acid bases. We're just starting the MCQ, so we're on question number 1. It looks something like this. All right, let me get into some explanation on this question because this needs some understanding. Okay, so Kw is equal to the concentration of H plus and the concentration of OH minus, yeah? But so Kw is when your water is neutral, when you have equal amounts of both of these substances. Now, but Kw is also equal to this number, 1.0 times 10 to the negative 14. By the way, when you put that in your calculator, don't put 1.0 times 10 to the negative 14 and put it into parentheses. Just put 10 to the negative 14. Look, any number times 1 is itself, but anyways, I'm not going to get crazy on you or anything. But okay, see this H plus and this OH minus equal this thing. But see, the H plus and the OH minus both come from water, right? Because the water is breaking down into those two substances, right? H plus and OH minus. So the point is this, that this ends up being over here x squared, right? So the square root of both is, the square root of both, or of this number is 1.0 times 10 to the negative 7. So you have 1.0 times 10 to the negative 7 of H plus, you have 1.0 times 10 to the negative 7 of OH minus. Now, you might have remembered from the Henderson-Hasselbalch that pKa is equal, here, let me find some room to do this. pKa is equal to the negative log of Ka. Well, that makes, in this situation, if you took the pKw, you would have the negative log, at least at 25 degrees Celsius, of 1.0 times 10 to the negative 14. So your number would be 14 here, okay, of normal Kw. All right, let's see what I need to keep for you. Let's look at this question. Okay, so this question says, the ionization of water is represented by the equation above. Values of pKw at various temperatures are listed in the table below. So notice what's happening. As temperature is increasing, pKw is decreasing, right? And you'll also notice there's one number that's missing that we would like to that would make this really easy, or we could see it a little bit easier. There's the room temperature, 25 degrees Celsius, because that would be 14.0. Oh, so see, you're missing that one value. Okay, based on the information above, which of the following statements is true? The dissociation of water is an exothermic process. No. The pH of pure water is 7 at any temperature. Well, no, it wouldn't be 7 at any temperature, because what this is saying is at different temperatures, the Kw, like Kw at 25, might be this 1.0 times 10 to the negative 14. But the Kw at, let's say, 40, according to the table, is equal to 1.0 times 10 to the 13.5, or the negative 13.5, right? Now, that doesn't mean that, okay, that still means that the absolute, the concentration of H plus and the concentration of OH minus is equal to 1.0 times 10 to the negative 13.5 at that temperature. Now, what that means is X at that temperature is 1.0 times 10, remember you got to square root it, to the negative 6.75. So what's the pH here? The pH here, if you took the negative log of that, would equal 6.75, right? And you're saying, oh, it's becoming acidic. No, it's not becoming acidic, because what's the pOH? The pOH is also 6.75. Look, this H plus over here equals 1.0 times 10 to the negative 6.75. But guess what? This OH minus as well equals 1.0 times 10 to the negative 6.75. So no, it didn't become acidic. It's still neutral. Neutral is now 6.75 in this situation. The overall pH plus POH is 13.5. So this is a really interesting question. So, okay. The pH of pure water at 7 at any is the pH of pure water is 7 at any temperature. No, that's wrong. I just showed you that the pH will be 6.75 at 40. As the temperature increases, so as temperature is increasing, the pH of the water increases or the pH of water decreases. Okay, the answer is D. Okay, the pH of pure water decreases. Now let me tell you why you're confused. Right now you're thinking, wait, or what you should be thinking is, as the temperature increased here, right, my pH my pH decreased there because it is part of the KW. It's going to go this way. It's going to become 6.75. But if you went from 0 degrees Celsius, it would be 14.95. So you can use that square root and you'll get your correct answer. The answer is D. Number 2. Okay, NOBr yields 2 NOs and Br2. Look, that first question took much longer than most ones, but this one you'll be okay. All right, the equation above, oh, you know what? This is funny. This is not an acid-based question, but let's do it anyway. The equation above represents an elementary step in the chemical reaction. Which of the following is the correct expression for the rate law of the elementary step? If you guys remember, this is from your kinetics. If this is the elementary step, then your elementary step is your rate is equal to K times the concentration of your NOBr squared. That's it. It's that easy. It says it's an elementary step, so there you go. The answer is C. All right, question number 3. All right, now you have this formula, and you want to be able to read this. Again, this is actually not a acid-based question, but that's okay. You know, it's good for us to review this stuff too, so I don't mind. All right, if the standard molar heats of formation of ammonia, NH3, and gaseous water, H2O, are negative 46 kilojoules per mole, okay, and negative 242 kilojoules per mole, respectively, what is the value of delta H? They gave us the delta H's, the heats of formation. So this delta H is equal to H of your product minus H of your reactant. Now, there's another way to calculate delta H, which is bonds broken minus bonds formed, but that's not this question. This one is giving your delta H's. And it's saying that the heat of your product, let's see, what's my product? My product is H2O. And H2O happens to be negative 242. Now, the product of my reactant is NH3, and NH3 is negative 46. So let's get that color. You have negative 46. You have products minus reactants. Now, what I also want to share with you is like, okay, there's a couple things. Why doesn't O2 or N2, why don't they have any delta H? Well, O2 is a pure substance, so its delta H is 0. N2 is a pure substance, so its delta H is 0 as well. Now, there's one last thing you need to account for. That's a 4 and that's a 6. Those are coefficients that need to be multiplied here. Oh, I didn't write this, 46, sorry. Okay, so now remember, this is the AP exam and this is a multiple choice question. This is non-calculator. So this is, I end up estimating this at negative 250 minus 4 times negative 50, right? 250, what's 6 quarters? That's $1.50, so this is 1,500, and that's negative. This is going to be positive 200, and the answer is going to be somewhere around negative 1,300. The answer that's close enough is D. Okay, so I'm just trying to show you the way I use estimation techniques. One of the things that you're going to find that is really against you on the AP exam is time. But okay. Okay. Number 4. you have this big, huge formula, back to acid bases. In a titration experiment, H2O2 reacts with aqueous MnO4 as represented by the equation above. The dark purple KMnO4, and remember the K, we are going, where is that? No, that's the spectator. This KMnO4 is the MnO4 minus. Solution is added to a burette to a colorless acidified solution of H2O2 in an Erlenmeyer flask. So H2O2 is colorless. Okay, MnO4 is purple. Okay, solution is added to burette to a colorless acidified solution of H2O2 in an Erlenmeyer flask. At the end point of the titration, the solution is a pale pink color. Which of the following best describes what happened to the pH of the H2O2 as the titration proceeds? As the titration proceeds, let me show you something. I noticed that we were an acid in your reactants, and then it becomes a liquid. Okay, sorry, H2O. So look, all I know is the left side was an acid, the right side seems closer to neutral. So in other words, we are becoming less acidic. Yeah, we're becoming less acidic. We're becoming, I'm going to say basic, but less acidic is probably the right way to say that. All right, the answer, which of the following best describes what happens to the pH? Well, what happened to the pH? If we were acidic, we were a really low number, like we were 1 through, let's say 6.9, right, 6.99. And then we became neutral, we became like water. Like so in other words, our pH is starting to increase. All right, A, the +2 charge on the manganese ion maintains the acidity of the solution. I don't know what that means. It didn't maintain its acidity. The production of water dilutes the solution, making it basic. It didn't become basic, okay? It didn't, there's no OH minus there. It's just getting less acidic. As the H plus ions are consumed, the solution becomes less acidic and the pH increases. That is true. That's exactly what we're trying to say there. So no, no, and no, okay? Okay, D is saying pH decreases. When pH decreases, that means you're getting more acidic. And people get confused with that all the time, so try not to make that mistake. Okay, number 5, much more traditional problem of of an acid base. Okay, you have a weak monoprotic acid, HA, and that is yielding H plus and A minus. In a 0.10 solution of weak monoprotic acid has a pH equal to 4. The ionization constant Ka of the acid, so Ka is equal to the concentration of H plus times the concentration of A minus over the concentration of your HA. All right. A 0.1 solution of weak monoprotic has a pH equal to 4. Well, if your pH is equal to 4, you know what? You could find out what your concentration of your H plus is. Your concentration of H plus is equal to 10 to the negative pH. So in other words, the H plus value, and this is a little large. Let's shrink everything down a little bit. Okay. So if you have this as your H plus, you know that your H plus and your A minus are both equal. So let's say this is going to be 10 to the negative 4, and this is going to be 10 to the negative 4. And what is your HA? Your HA is 0.1. Now some of you might be confused. Why are they both? Why is the H plus? Oh, that's a bad color to use there. Let's use something like this. Why is the H plus and why is the A minus? Why are those two things both the same? Well, remember, they came from the same source, right? So if you had 100 of these, you know, and then 50 of these were created, well then 50 of these were created as well, because they're coming from the same place. They're disassociating from the same place. So if you had 10 to the negative 4 of the H plus, then you have 10 to the negative 4 of the A minus. And the HA, I'm getting that number right here from here. All right. All right, now, again, non-calculator section. So let's, I kind of manipulate these numbers to be 10 to the negative 4, 10 to the negative 4, and I manipulate that bottom one to become 10 to the negative 1, right? you do that top part, it becomes 10 to the negative 8 over 10 to the negative 1. Remember, when you multiply bases, you add their exponents. When you divide bases, you subtract them. So this is going to become 10 to the negative 8 minus negative 1, which is 10 to the negative 7. Answer C. It's a good question. This is more straightforward, not a lot of concept, but notice the math. The numbers are very doable, and you don't require a calculator to get that answer. All right, let's go to number 6. Okay, this was super interesting. Okay, before you even start, look at the pHs of these 4 acids. You have acid 1, 2, 3, and 4, and you're going to notice a number that is the most glaring number in this whole group. I would say that 0. It had a pH of 0. Well, if it had a pH of 0 at a concentration 1, if you've ever done the pH is equal to the negative log of 1.0, like a molar of 1, like a concentration of H plus that is a 1, then you're going to find out that you will get a pH of 0. That's pretty acidic. That means you're dealing with 1 molar HCl, or hydriodic or nitric acid or something like that. Something that is strong. And if you remember your strong acids, that's I give my students this. I say brickle no so clo. Say it with me. Brickle no so clo. Okay? These are your strong acids. And look, it's easy to know which ones the weak acids are because everything is weak except for these 6. These are the 6 only strong acids. Now, I know that if this thing reached 0, this one out of all of them is one of these from the top. Okay? It is a strong acid, acid number 2. Acid number 1 is weak, acid number 2 is strong, this is weak, and this is weak. Okay? You see that number 0 and you're like, whoa, how did the pH get that low? And it really got that low because it's a strong acid there. All right, the pH of solutions of 4 acids prepared at various concentrations were measured and recorded in the table above. The 4 acids are in no particular order: chlorous, hypochloric, lactic, and propanoic. That's funny because hydrochloric right there is the strong acid, and it happens to be the second one on the list. So maybe that's specifically that list. But hydrochloric is the strong acid there, HCl. A 25 milliliter sample of a 1.0 molar solution is mixed of acid 1. So, okay, what does that mean? This is a weak acid. Is mixed with 25 milliliters of 0.5 molar NaOH. Oh shoot, this is so much to explain. Okay, this is a strong base. All right, before I can even answer this question, let's talk about what we're talking. Man, there's a lot. Okay, this is going to take me a little bit of time. All right, let's talk about how the mixture stays this way. But this is going to actually answer more than one question, so it's actually very worth it that I do it. All right, when you have a strong acid, strong base, okay? Strong acid, strong base. It's going to be a lot different than a weak acid, strong base. Let me show you why. A strong acid, strong base looks something like this, okay? A weak acid, strong base does something like this, okay? There's 2 things going on here. Now, I want you to think what a strong acid is. You have, okay, let's say you have HCl, and it's going to become H plus and Cl minus. If we did an ice table, which we can't because this thing doesn't go to equilibrium, but if we did, let's say we had 100 of these, we had 0 of this, we had 0 of this went down by x, this went up by x, and this went up by x. Then this would go all the way down to 0, this would go all the way up to 100, and this would go all the way up to 100 because a strong acid disassociates completely, okay? Now, on the other hand, you have HA, and HA is much more funny. Okay, when you have a weak acid, notice that I'm going to use a double arrow here instead to become H plus and A minus. That means it's at equilibrium. Now we can do an ice table. Now I'm going to use just some random numbers. Okay, this is 100, this is 0, this is 0. If this goes down by x, this goes up by x, and this goes up by x. Let's say this E goes to 70. I'm just putting a number out there. This goes to 30, and this goes to 30 This is the way that worked, okay? So the point is that strong acids like HCl disassociate completely. Weak acids don't disassociate completely. But when you have this graph of a strong acid being titrated with a strong base over here, you get this very smooth curve that kind of just goes, up like this, okay? And your equivalence point is right here. That equivalence point, that EQ point, is equal to 7. Strong acid, strong base, they're equal to 7. But that HA, because what is the equivalence point? That is when your moles of each substance are equal. So a lot of times we solve our equivalence point by M1V1, M2V2. Right, but this weak acid, on the other hand, okay, look at what it does. As you start adding OH minus, okay, now think about this, okay? This is a strong base, it's a weak acid, strong base. Okay, when you have a weak acid and strong base, and you have this weak acid HA, and you start adding OH minus. When you start adding OH minus, that OH minus starts to consume the H plus. So think about Le Chatelier's principle. You have HA, you have H plus, you have A minus. Okay, we're going to start getting rid of this H plus. What's going to happen to the Le Chatelier seesaw? It's going to do that. The right side is going to get lighter because the OH minus is consuming the H pluses. It's taking the H pluses away. So what will Le Chatelier's principle do here? It will relieve the stress on the system and get back to equilibrium by producing more H plus, more A minus. So that's what's happening right here. Okay, right there, you're seeing us adding OH minus. Okay. Okay, let me see. Right here, where I marked in orange. Let me do a different color. I forget these highlighters don't work when I do that white. Okay, that place right there is when we start consuming H pluses using OH minus, and the reaction starts creating more H plus. It's resisting change. It's resisting change. It's resisting change. That's where we are buffering. Okay, that's where we're buffering. That's where we're resisting change. And because we resisted change, when you have a weak acid and a strong base, guess who wins? The strong survive. Okay, that means your EQ point when you had equal moles of your strong base and your weak acid. When you did equal moles of your strong base and your weak acid, what happened was, your equivalence point is greater than 7. Think about it. Strong base, weak acid. Strong base wins. It's going to be more basic than acidic. I'm trying to write acidic there. So the equivalence point is going to be greater than 7. Okay, I just taught you a whole lot of stuff. Let's see how many questions that was worth. All right, let's read this one. Ooh, okay. Okay. Now I want you to notice the numbers. You have 25 milliliters of 1 molar solution of a weak acid, and you have 25 milliliters of 0.5 of NaOH. Okay, that's not equivalence. That you have not reached equivalence. You've actually only reached the halfway equivalence point. Like, this is 25 times 1, this is 25 times 0.5, so we're still in the buffer zone, in other words, okay, with this weak acid and strong base. Okay, which of the following best explains what happens to the pH of a mixture when a few drops of HNO3 are added? Now, NO3 is a strong ion, it goes away. So we're basically adding 1.0 H plus. Well, what is a buffer for? A buffer is to prevent, it helps prevent drastic changes in the pH. So in other words, what happens when we add 1 molar of HNO3? Not much to the pH because we're still in the buffer region, okay? So as the pH of the mixture increases sharply, nope. The pH of the mixture decreases sharply, nope. The pH of the mixture stays about the same, okay. The pH of the mixture stays about the same, so it's between C and D. Let's get rid of A and B. The pH of the mixture stays about the same because the conjugate base of acid 1 reacts with the added H H3O plus ions. That is true, okay? Because you're going to go like this. You're going to have your HA, you're going to have your H plus and your A minus. Some of that H plus was taken away, right? Some of that stuff went away. But now we're adding them back using the HNO3 here. We're going to add them back into there, and it's going to react with this conjugate acid to go backwards. So yes, the correct answer is C. But the wording is a little funny. Now, I also want to show you D, okay? The mixture of the mixture stays about the same. That's true because the OH minus ions in the solution react with the H3O plus ions. What OH, what OH minus? The OH minus we're consuming H plus is becoming water. So we're still before the equivalence point. So there's no OH minuses that are left for us to use that way. So, all right, let's go to number 7. Using that same information from that data, and remember, this data is saying that acid 2 was our strong acid. Acids 1, 3, and 4 are weak, and we know that, okay, and we're confident about that. There's not a lot of questions of if that's true or not. We know that's true. All right, of the following species, what has the greatest concentration in a 1 molar solution of acid 1 at equilibrium? Okay, so this one was a little bit more, okay, there's a really involved way to do it. I said to myself, okay, so acid 1 is like some HA yielding H plus and A minus. Ooh, what am I drawing? Okay, and this is in some form like this, okay? Now, if I wanted to do it, it has a okay, so at 1 molar, if I wanted to do the Ka, right? At 1 molar of the acid 1, I was at 2.44. So that means this. If I wanted to do the Ka, I could solve for it. How much H plus A minus, and and then this is your HA. Ugh, I wrote plus, I meant concentrations, and I have to multiply these. Okay. Now, my H plus, let's say it would be 10 to the negative 2.44. My A minus would be the same, so this is squared, and then this is 1.0. Okay, I don't know. I don't want to mess. I don't want to do these numbers. Okay, every time I say that, I've already done it in my head. So, what are you gonna do? The curse. Being obsessed with doing math. All right, it's going to be 10 to the negative 4.88 over 1, right? Okay, so Ka is 10 to the negative 0.488. I don't know what that number turns out to be, but the Ka, this means that this is some kind of fraction, right? It's some kind of number over, some kind of number, right? So because of that, I know how do we calculate Ka? Ka is products over reactants. In other words, this thing has a lot more reactants than products. It has a lot more HA than H plus or A minus. So let's look at the answers to number 7. It says, what is the thing that it has most of? Does it have most OH minus? No. Well, no, it doesn't, because it doesn't have any OH minus. It's an acid. Okay, it has like trace amounts. It doesn't have it has H3O plus, but like we said here, there's less H3O plus than there is HA. Okay, the answer is C. Number 8. If equal volumes of 4 acids at the concentration of 0.5 molar are each titrated with a strong base, which will require the greatest volume to reach the equivalence point? Think about what equivalence point is. Now, strong acid, strong base. Oh, okay. Let's strong acid, strong base, the equivalence point is 7. A weak acid, strong base, the equivalence is above 7. However, they happen when when you find it by M1 V1 is equal to M2 V2. Both of them are found that way. What does that mean? When you have equal moles of the strong base and the strong acid, the equivalence point is equal to 7. But when you have equal moles of the strong base and the weak acid, your equivalence point is above 7. But either way, you had equal moles, okay? The point is, all acids require the same volume of base to reach the equivalence point. They all require the same amount of base. Equivalence point is when you have equal amounts of the substances, not whether they got to 7 or not. And that's where students get confused. Students think equivalence point is when their amounts equal 7. No, it's when their amounts are equal and their equivalence points will shift based on that. So the correct answer is D. Number 9. For which acid is the value of the Ka dissociation constant, Ka, the smallest? Okay. Now, I want to let you know something. When you do this one, I want you to think about what the H plus is. Okay. In acid A, it's 10 to the negative 2.44. Now, you guys see where I'm getting that from? At 1 molar. Okay. At 1 molar, acid 2 is 10 to the 0. At 1 molar, acid 3 is 10 to the negative 1.92. And at 1 molar, this is 10 to the negative 0.98. Okay? Now, this is all from the chart. Where is that chart? Here you go. I'm getting these values from here. Okay? At 1 molar, 2.44, 0, 1.92, 0.98. Okay, that's where I got these numbers from. Now, who created the most H? I don't know what this number is, but I know that this negative means it's like some fraction. It's like 1 over 1,000, right? This is like 1 over like 100, and then this is like 1 over like 10. Okay, but I know that this is like 1 over 1, right? So the point is this: who has the most H plus? The most H plus, who? This has the most H plus. It created the most H plus, right? It's a 1-to-1 ratio. Who has the least H plus? It would be the opposite. It would be this number because that's the largest, okay? The correct answer, if you have the, okay, and what does that mean? If you have the most H plus, that means you disassociate the most, meaning your Ka, how do we find Ka? Ka is equal to products over reactants. If Ka is equal to products over reactants, look, this has a whole lot of product, or it has, okay, Ka has more product than, of acid 2 has more product than acid 1, 3, or 4. Who's the smallest? The answer is A. A does not disassociate that much. It does not form a lot of product, and the product in an HA, one of the products is H plus. So I just did this by calculating the H plus. Who had the smallest H plus? The smallest H plus would be acid A, or acid 1. Which of the 4 acids listed on the table is hydrochloric? Hey, we already did that one, right? It's acid number 2. How do I know that? Because at 1 molar, its pH was equal to 0. It was a strong acid. All right, number 11. Finally, we got, that was a lot. That one question, bled into 4 different questions, and they were all intricate on their own, and that's a kind of staple of the AP exam. It's not an easy exam. It really isn't, and they really know how to ask questions to get you thinking. All right, a solution is prepared by adding 100 milliliters of 1.0 molar acetic acid to 100 milliliters of 1.0 NaC2H3O2. The solution is stirred and its pH measured to be 4.73 after 3 drops of 1 molar HCl are added to the solution. The pH solution is measured and is still 4.73. Which of the following equations represents a chemical reaction that accounts for the fact that the acid was added but there is no detectable change in the pH? Okay, if there is no detectable change in the pH, then this is what we call a buffer. And okay, that means you have your acid HC2H3O2, and you have your anion, okay? You have to have these two things. Look, when you have a buffer, think about it. If you have this and this, okay? If you preload, let me show you. This is how I like to show buffers working. You have HA becoming H plus and A minus, right? Let's say we know that you're already going to take away a bunch of H pluses because you're going to titrate this with a bunch of OH minus. If I add a bunch of OH minus, yeah? If I add a bunch of OH minus, what's it going to do? It's going to consume that H plus and take it away. And what would it do? It'll make your Le Chatelier's seesaw go up on the right side. You don't want that to happen. You know what? One way I could preempt. Okay, this guy's planning on taking my H pluses away, and I don't want it to affect my equilibrium. What you could do is preload it with a bunch of HA and preload it with a bunch of A minus. That way, if you take, there's only a little bit of H plus. If you take that H plus away, it will stay at equilibrium. This is what a buffer does. So your goal is to keep a lot of your acid and a lot of your conjugate base, right? You remember early on in this unit, this is your acid, this is your conjugate base, right? It's acids donate protons. So if you front load at the very beginning, and when you have your acetic acid, you add a bunch of acetate, right? The conjugate base, you will prevent, when you start titrating it with a strong base and you start taking those H pluses away, you're going to prevent a lot of change there. So what is happening? Okay, which one shows a buffer? The correct answer here is, it's here. Notice you have your acetate. Now, okay, I really don't like this. They should show a double arrow here. That's a problem for me personally. But here, notice that the acetate is accepting H plus ions. That's not what it does. That's incorrect here. And then what the heck? What's going on? Where did the Cl come from? Oh, I see. And then this is water. No. We're dealing with having acetate and its buffer. Okay. All right. Let's take a look at question number 13. Okay. A solution is prepared by mixing 50 milliliters of 1.0 sodium, whatever that is, with 50 milliliters of sodium 2, whatever that is, on the basis of information above. Which of the following species is present in the solution in the lowest concentration? All right. What is Ka? Ka is equal to products over reactants. Okay, Ka is equal to products over reactants. Look at the first Ka. Is there more product or is there more reactant? There is way more reactant. That's why this number is negative, right? This exponent. Okay, look at Ka2. What is this? There is, again, way more reactant because that is negative. And the last one, there is even more reactant. Okay, so more reactant. Okay, so in the first equation, there's more of this than H2PO4. And then there's more of this than HPO4. Then there's more of this than PO4 3 minus. So what's the thing that they have at least? Well, if it's always doing more reactant, guess what? The last product, there's like none of that, okay? Because, look, this is the highest number, this is the second highest number, this is the third highest number, and then this one, it just never happened. So the correct answer, D. There's almost no product, okay? Yeah, with the little bit of the H2PO4 we had, we made even less HPO4. And with the little bit of HPO4 we had, we made even less PO4 3 minus, so the answer is D. 13. A solution of a weak monoprotic acid is titrated with a solution of a strong base, KOH. Consider the points labeled A through E on the titration curve that results as shown below. The point at which the moles added to the strong base are equal to the moles of the weak acid initially present. Hey, we just talked about this. When your moles are equal, M1V1 is equal to M2V2. Can I do something here that I don't know how many of you guys actually know? Look, molarity is moles over liter, yeah? Volume is liter. Oh, guess what? That gives you mole. Molarity is moles over liter. Liter, volume is liters, so that cancels out, and then you get mole. Oh, what the heck? M1V1 is a way to find your moles. M2V2 is a way to find your moles. When you multiply concentration by volume, you get rid of the liters. Anyways, that is known as C. Okay, at which point the moles of the added strong base are equal to the moles of the weak acid. When the moles are equal, that is called your equivalence point, C. 15. A solution of strong weak monoprotic acid is titrated with a solution of a strong base KOH. Consider the points A through E titration curve. Okay, the point where the pH is close to that of the strong base being added. Well, that just makes sense that the strong base is probably up here, right? This is what the strong base is. Now, it's not exactly at E, but it's closest to it because, look, the only way you could get a low number to increase is if you're increasing it with something that's incredibly high. Now, the reason why I say that the strong base is a little bit higher than E is because we did add a weak acid to it. We did lower its OH a little bit. All right, number 16. A solution of a weak monoprotic acid is titrated with a solution of strong base, KOH. Consider the points labeled A through E on the titration curve that results as shown below. The point at which the concentrations of the weak acid and its conjugate base are approximately equal. That is the definition of what we call the halfway equivalence point. The halfway equivalence point is here, B. Now, how do I know that? Let me show you. See this? That's the equivalence point. It happened at 100. Guess where the halfway equivalence happens? At 50. Oh, okay, that's a halfway equivalence point. Now, the halfway equivalence point is really special in the Henderson-Hasselbalch. Let me explain this. The Henderson-Hasselbalch says that pH is equal to pKa plus the log of A minus over HA. Okay, so when you have this, pH is equal to pKa plus the log of A minus of HA, notice something weird happens. Your pH is equal to pKa when I can get this guy to equal 0. How do you get the log to equal 0? Now, you might not be great at logs. Okay, let me show you. If you have a log of, you have a log of 1, that is equal to 0. Okay, so when is your log going to equal 1? Well, that is when A minus is equal to your HA. Okay, so when you have your A minus equal to HA, then that makes when these two things are equal right here, that becomes 1 over 1. That means the log of 1 becomes 0, nullifying this altogether, and then your pH is equal to your pKa. Now, I want you to also think about this. Okay, I should go this way. How do you get a negative from your log? Let me show you. If your A minus over your HA is greater than 1, right? This thing will become positive. If your A minus over your HA is less than 1, and I don't mean a negative number, I mean a fraction. Less than, if you use a negative number, logs don't understand negative numbers, okay? So you have to do this, through your through your A minus and H plus. All right, let's get back to this question. The point at which the concentration of the weak acid and its conjugate base, the weak acid, the HA, and its conjugate base, the A minus, are approximately equal. That's called the halfway equivalence point. That answer is B. All right, number 17. A solution of 10 molar or 10 milliliters of 1.0 molar HCl and 10 milliliters of 1.0 molar NaOH has the pH of what? Now, okay, look. First of all, just looking at it, I could see that there's more NaOH. So I know the thing's going to be basic. So look at your possible answer choices. It can't be 0, it can't be 1, it can't be 7. It has to be 13 or 14 because it has to be basic. Why does it have to be basic? I have more base than I do acid. So how much more? All right, let's find out the molarity. So how many moles? Moles are equal to molarity times volume, yeah? So if I have 0.01 times 1, then my moles is 0.01. If I have 1.2 times 0.01, then I have 0.012, right? So look at these numbers. Look, how much more base do I have than acid? I have 0.002 more moles of NaOH. Why is that important? I'm running out of space. Okay, why is that important? Because that means, okay, look, think about it. HCl, strong acid. NaOH, strong base. When you combine those together, you're going to form water. It's going to become neutral. But this is more basic than it is acidic, right? Your NaOH is 0.002. Now, your volumes are additive, so you have 0.002 moles of NaOH. First of all, let me tell you something. All right, well, okay, your volumes are what? 0.020 because I made them liters, right? I added the 10 milliliters to the 10 milliliters. Okay, so when you get this, this is like saying 1 over 10, which is 0.1. Now, I know in my mind that pH is 14 when I have 1 mole of NaOH, but I don't have 1 mole of NaOH, so the answer has to be 14. Here, you have to take the negative log of this. The negative log of 0.1 is going to be 1. And what did you find? You found your POH because you're taking the 1 mole, 0.1 mole of OH minus. So my pH is my POH is 1. If my POH is 1, well, pH plus POH is equal to 14. That means my pH is 13. So the answer is 13. Okay. Okay, we're almost there. Okay, let's see another chart. Again, a weak acid and strong base. pH versus volume titrant. Oh, I'm going to tell you about this about the last question. I didn't even do it. Okay, I knew it wasn't going to be A, B, or C. I also knew that 14. If for it to be 14, it had to be 1 molar, and I knew I was only going to be 0.2 molar, I only had 0.2 moles. So I was like, you know what? It's going to be 13. So there's a little bit of logic that you could use, but I don't think many of you guys are going to be that confident in your math at that time. But yeah, let's see. All right, pH versus volume titrant added. Okay, 50 milliliter sample of HA has an unknown molarity, is titrated, and the pH of a resulting solution is measured with a meter and graphed as a function of time of 0.1 molar NaOH. Okay, all right, let's make some space. Yeah. All right, a student carries out the same titration but uses an indicator instead of a pH meter. If the indicator changes color slightly past the equivalence point, what will the student obtain for the calculated concentration of the acid? Okay, this was cool. So what I did was I set up an M1V1. Okay, and I said, okay, we know that this is 50 and milliliters, but we don't know it's molar. We know that this is 0.1 molar, and this is 40. Wait, you guys are going, where did you get that 40 from? Look at the graph. That's the equivalence point. That's what I'm supposed to use, M1V1, N2V2. Ooh, so that gave me a number. Okay, so now I'm going to do this. Now, when I do this number, it turns out that I get 4 over 50. And some of you guys are going to be like, why didn't you change that to liters? Why did you leave them in milliliters? Well, if they're both milliliters, it's fine. So the 50 and the 40 are fine keeping them that way. Anyways, this is going to turn to 0.080. Yeah? So, okay, the answer has to be A or B. And you're going like, wait, which one is it? Now, I want you to logically think about this. And this might, okay, it says if the indicator changes slightly past the equivalence point, So if it's slightly past the equivalence point, then that means we added a little bit, we added a little bit more NaOH, meaning the calculation is calculating for a little bit more H+. The answer is B. Okay, if you don't get that, just like think about it. I mean, you'll get it. Like it's a really weird thought process. Okay, 19. At point R, the titration of which of the following species has a concentration? Let's look at R. Where's R? Oh, shoot. R is way at the beginning. Yeah? Look, S, if this was the equivalence point, then this is S is the halfway equivalence point because 40 and 20, right? But R is even before the halfway equivalence point. Look, halfway equivalence point is when A minus is equal to HA, right? This is where we still have more HA. We haven't reached the halfway equivalence point when we're at R. So the answer has A. We're not at the halfway point yet. Number 20. At which point on the titration curve is A minus close to twice that of HA? Twice that of HA, okay, you got to be past the halfway point. Yes? That is T. Past the halfway. You know, they're saying, how is that half? Well, the only other choice you got is U, and then at that point you don't have anything. Like all that stuff has been buffered out, right? All that HA is gone. So the answer is T.